All right, let's get right into it. Hiding in plain sight, right in our own sun, there's this absolutely beautiful cosmic mystery that scientists have been trying to puzzle out for decades. It's a story that isn't told with words, but with a pattern of magnetic fire that, you won't believe this, looks just like a pair of butterfly wings.
And this is our main clue. This incredible image is called the butterfly diagram. It's basically a map of where sunspots pop up on the sun's surface over the years. Time moves from left to right, and the latitude goes from the North Pole up top to the South Pole at the bottom. The pattern you see here? Well, that's the key to understanding what's going on deep inside the sun.
So, what's actually making this pattern? It all boils down to something called the solar dynamo. The easiest way to think about it is like the sun's magnetic engine. It's this super complex flow of plasma deep inside the star that's generating its massive, constantly changing magnetic field. And that dynamo, well, it's the engine driving everything we're about to talk about.
Okay, let's start with what we can actually see with our own eyes, or, our telescopes. For more than a century, astronomers have been tracking the sun's activity, and they've noticed this really consistent, predictable cycle. Here's how it unfolds. At the beginning of a new solar cycle, these sunspots, which are really just these super intense magnetic regions, they start appearing at the sun's mid-latitudes, about 30 degrees north and south. Then, as the 11-year cycle goes on, new sunspots show up closer and closer to the equator. And when you plot all that data over time, you get this gorgeous drifting pattern that forms the butterfly's wings.
But here's the thing, there's a problem, and it's a huge one. Even though we can see this pattern perfectly clearly, our best scientific models of the sun have really struggled to replicate it. It's like a crucial piece of the computer code has been missing all this time.
So take another good look at the real data. Because when we put it side by side with what our computer simulations spit out, something just doesn't line up. Can you see what the models are getting wrong? Now check this out. On the left, that's the real deal, the actual sun. You can see the main wings drifting down to the equator, for sure. But look closer. See those fainter branches of the magnetic field that kind of peel off and rush up towards the poles? Now look at the standard model on the right. The equatorial drift is there, yeah, but those polar branches, poof, they're gone, just completely missing.
This missing feature has a name, the rush to the poles, and it's not some tiny detail we can just ignore. This flow towards the poles is the very thing that cancels out the old magnetic field and builds up the new one. It's what causes the sun's entire magnetic field to flip every 11 years. So without it, our models aren't just a little off, they're fundamentally broken.
So the big question is, how do you fix the models? Well, a team of researchers decided to treat it like a detective case. They came up with 3 potential suspects, 3 different physical ideas that might be the culprit behind that missing rush to the poles.
Okay, here are the 3 main suspects they put to the test. First up, the location theory. What if the model just needs a simple rule that forces sunspots to show up at lower latitudes? Suspect number 2, the strength test. Maybe magnetic fields have to get super strong, reaching some critical point, before they can actually punch through the surface. And finally, suspect number 3, the buoyancy factor. This idea says that magnetic fields are naturally buoyant, kind of like a cork in water, and the stronger they get, the faster they rise.
So they plugged each of these theories into their models one by one and compared the results to the real sun. It was time to find out which one, if any, could finally crack the code.
Well, the first 2 suspects didn't really pan out. The location theory, yeah, it created a rush, but the magnetic field it predicted deep inside the sun just didn't match what we observe. The strength theory kind of worked, but it was incredibly finicky. You just tweak one little number and the whole model just falls apart. Not a very reliable solution, right?
But then they tried suspect number 3. They tweaked the model so that the stronger the magnetic field gets, the more buoyant it becomes and the faster it rises to the surface. And when they ran that simulation, everything just snapped into focus.
And this right here shows the result perfectly. On the left, there's the real sun again. And on the right, the new model with magnetic buoyancy baked in. Just look at that. It is almost a perfect match. The wings are drifting to the equator, just like they should. And, critically, those faint branches rushing up to the poles are finally there. The model suddenly looks just like the sun.
And don't just take my word for it. The scientists themselves knew they'd found the breakthrough. In their own words, they said that magnetic buoyancy is the most promising idea because it's the one that consistently creates the most realistic, solar-like butterfly diagrams. Mystery solved.
Okay, so this is great. We found the missing piece of the puzzle. But you might be wondering,
Why does getting this one little detail in a diagram right matter so much? What's the big deal?
So, let's just recap what we figured out. First, that rush to the poles isn't just a minor detail. It's an absolutely critical part of how the solar cycle works. Second, we're now pretty sure that a simple physical process, magnetic buoyancy, is the reason it happens. And finally, by adding just this one ingredient, our understanding of the sun's magnetic engine just took a major leap forward.
And here's the really big payoff. Because this buoyancy model works so well, it gives us a huge clue about where the sun keeps its most powerful magnetic fields. This image shows what's called the toroidal field. It kind of wraps around the sun like a bunch of rubber bands. And this new result strongly suggests it's all being generated and stored deep inside the sun, right near the equator. We're essentially using this model to see inside a star. It's incredible.
So, you see, cracking the code of these magnetic butterflies did way more than just solve a pretty puzzle. It's given us a much better, more accurate tool to study our own star, and it leaves us with a really exciting question to think about. Now that we have this more perfect model in our hands, what other long-standing secrets of the sun are we finally going to be able to unlock?